Hello students. Hello and welcome to this video. In this video we will start with matrices. We have covered till determinants, so this is the last chapter before we start with miscellaneous problems, and theoretically this is the last chapter, and we will take probably two videos to finish the theory part of it. So the link to download the PDF will be in description, as well as at the end I will show you how you can download and maintain a updated copy of the PDFs. I will also show you my question answer website where you can come and ask questions. That is, if you don't enjoy the AI conversation and you want human conversation. So without further ado, let's get started. So I will read through and you follow along, or you can pause and read the theory yourself, however you like, or you can download the PDF and read that. So without further ado, let's get started. Matrices are an important concept which has numerous real-life uses in various mathematical branches. Also, it has huge importance in modern computer science. It has its applications in computer graphics, artificial intelligence, data structures leading to various clever algorithms. Thus, it is of paramount importance that the reader understands this particular concept in a sound manner. Definition: a matrix is a rectangular array of real or complex numbers. This rectangular array is made up of rows and columns much like determinants. Let us consider a matrix of m by n symbols, where m is the number of rows and n is the number of columns. This column shouldn't be there. So our matrix is A11, A12 up to A1n, and column wise it is A11, A21 up to AM1. So this mth row and mth column element is AM1. Such a matrix is called m by n matrix, or a matrix of order m by n. Sometimes a matrix is shown with parentheses, as is missing here, instead of square brackets as shown in last example. A compact way to write a matrix is A is equal to Aij within brackets, where I varies from 1 to m and j varies from 1 to n, or simply Aij within brackets with m by n in subscript. Aij is an element located at ijth row and jth column and is called ijth element of the matrix. A matrix is just a rectangular array of numbers. Unlike determinants, it does not have a value. So now we have classification of matrix, and first we look at equal matrices. Two matrices are said to be equal if they are the same order and each corresponding element is equal. Row matrix. A matrix having a single row is called a row matrix, for example 1, 2, 3, 4. Column matrix. A matrix having a single column is called a column matrix, for example 1, 2, 3, 4, like so. Square matrix: if m is equal to n, that is number of rows and columns are equal, then the matrix is called a square matrix. For example 1, 2, 3, 4, 5, 6, 7, 8, 9 is a 3 by 3 matrix. Then we have diagonal matrix. The diagonal from left hand upper side corner to the right hand side lower corner is known as leading diagonal or principal diagonal. In the example of square matrix, the elements of the diagonal are 1, 5, 9. When a matrix has elements, all elements are 0 except those belonging to its diagonal, then it is called a diagonal matrix. Equivalently, we can say that a matrix Aij m by n is a diagonal matrix if Aij is equal to 0 for all I is not equal to j. For example, the square matrix example can be converted to a diagonal matrix like below. So compare with this matrix over here, and you compare it with this matrix. So 1, 5, 9 is the diagonal which is non-zero, all other elements are 0. For an n by n matrix, the diagonal elements are represented as d1, d2 up to dn. This diagonal is also written with a tag prefix like tag d1, d2 up to dn. Then we have scalar matrix. A diagonal matrix whose elements of the diagonal are equal is called scalar matrix. For example, all the elements are same of the diagonal 5, 5, 5. For a square matrix Aij of m by n order to be a scalar matrix, Aij is equal to 0 for I is not equal to j, and Aij is equal to m for I is equal to j for all m not equal to 0. Then we have unit matrix or identity matrix. A diagonal matrix of order n which has all elements of its diagonal as one is called a unit or identity matrix. It is also denoted by In. We can write it in a concise way just like we did for scalar matrix as Aij is equal to 0 for I not equal to j and Aij equal to 1 for I equal to j. Horizontal matrix. And m by n matrix is called a horizontal matrix if m less than n, for example, 1, 2, 3, 4, 5, 6. Vertical matrix, an m by n matrix is called a vertical matrix if m greater than n, for example, 1, 2, 3, 4, 5, 6. Triangular matrix, a square spelling is wrong. A square matrix in which all the elements below the diagonal are 0 is called upper triangular matrix. Conversely, a square matrix in which all the elements about diagonal matrix is called lower triangular matrix. Thus, for a lower triangular matrix, Aij is equal to 0 when I less than j, and for upper triangular matrix, Aij is equal to 0 when I greater than j. Clearly, a diagonal matrix is both lower and upper triangular matrix. A triangular matrix is called strictly triangular if Aij is equal to 0 for all I between 1 and n. Example of upper triangular matrix is given here, and example of lower triangular matrix is here. Then we have null or zero matrix. If all elements of a matrix is 0, then it is a null or zero matrix. Singular or non-singular matrix. A matrix is said to be non-singular if how do I read this? If the determinant of the matrix is not equal to 0, and singular if determinant is equal to of A is equal to 0. Trace of matrix. If some of the elements of a square matrix A lying along the principal diagonal is called the trace, that is, if TR of A. Thus, if A is equal to Aij n by m, then TR of A is equal to sigma I is equal to m Aii. Properties of trace of matrix. To prove the second and third properties of a trace matrix, we will have to use properties given further below on algebraic operations on a matrix. If A is equal to Aii of order n by n and B is equal to Bii of order n by n, and lambda is a scalar, then trace of lambda A is equal to lambda times trace of A. Trace of A plus B is equal to trace of A plus trace of B. Trace of AB is equal to trace of BA. Now we look at determinant of a matrix. Every square matrix A has a determinant associated with it. This is written as depth A or A within pipes. On keyboard, these are called pipes or delta. We observe following for determinants of matrices. If A1, A2 up to An are square matrices of the same order, then determinant of A1, A2 up to An is equal to product of determinant A1 times determinant of A2 up to determinant of An. If K is a scalar, then determinant Ka is equal to K to the power n times determinant A, where n is the order of matrix. If A and B are two matrices of equal order, then determinant of AB is equal to determinant of BA, even though AB is not equal to BA. Now we will look at algebra of matrices, and the first operation is addition of matrices. If any two matrices are of same order, then addition of those can be performed. The result is a matrix of same order with corresponding elements added. For example, consider two 3 by 3 matrices given below. So we have A is equal to A1, A2, A3, A4, A5, A6, A7, A8, A9, and B is equal to B1, B2, B3, B4, B5, B6, B7, B8, B9, Then A plus B will be A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, and so on. Subtraction is similar. Corresponding elements are subtracted here. So addition of matrices is commutative, that is A plus B is equal to B plus A, as well as associative, that is A plus B within brackets plus C is equal to A plus B plus C within brackets. Cancellation laws are true in case of addition. The equation A plus B is equal to O has a unique solution in the set of n by n matrices where O is null matrix. Scalar matrix, a scalar multiplication. The scalar multiplication of matrix A with the scalar lambda is defined as lambda of A is equal to lambda of small a ij. Multiplication of two matrices. The prerequisite for matrix multiplication is that the number of columns of first matrix must be equal to number of rows of second matrix. The product is defined as A of the order m by n and B of the order n by p is equal to sigma r is equal to 1 to n A mr B or p. It can be easily verified that the resulting matrix will have m rows and p columns. Now, properties of matrix multiplication are given here. Commutative laws does not always hold for matrices. If AB is equal to BA, they are called commutative matrices. If AB is equal to minus BA, they are called anti-commutative matrices. Matrix multiplication is associative, that is, if AB are multiplied first and then with C, that will be equal to BC multiplied first, then multiplied with A. Now, its proofs have been left for you as an exercise. Matrix multiplication is distributive with respect to addition and subtraction. That is, A times B plus minus C is equal to AB plus minus BC. Now, we have transpose of a matrix. Let A be any matrix, then its transpose can be obtained by exchanging rows and columns. It is denoted by A prime or A to the power p, or clearly if the order is of A is m by n, then A prime will have order of n by n. Now we have some properties of transpose matrices. A plus B prime is equal to A prime plus B prime. A prime and then prime of that is equal to A. A prime is equal to K A prime, where K is a constant. AB prime is equal to B prime A times A prime. Proofs are simple and it is expected of you to prove that. Then we have symmetric matrix. A square matrix capital A is equal to small aij is called symmetric matrix if aij is equal to ji for all ij. We can also say that spelling is wrong. We can also say that a matrix is symmetric if and only if A is equal to its transpose. Then we have skew symmetric matrix. A square matrix A is said to be skew symmetric matrix if Aij is equal to minus Aj for all Ij. Clearly, if a matrix is skew symmetric, then the elements of its diagonals are all zeros. Then we have orthogonal matrix. A matrix is said to be orthogonal if the product of matrix and its transpose is 1. Then we have a theorem. If A is a square matrix, then A plus A prime is a symmetric matrix and A minus A prime is a skew symmetric matrix. So we have proof A plus A prime, we take prime of that, so we get A prime plus A prime prime, that is A prime plus A. Hence A plus A prime is a symmetric matrix. A minus A prime, and we take transpose of that, that is equal to A prime minus A, which is equal to minus of A minus A prime. Hence A minus A prime is skew symmetric matrix. Now we have another theorem. Every square matrix can be shown as a sum of a symmetric matrix and a skew symmetric matrix. The proof is given here. Let A be any square matrix. Half of A plus A prime plus half of A minus A prime is equal to A. There should be a T here. Thus, the matrix A is a sum of symmetric matrix A plus A prime and a skew symmetric matrix A minus A prime. Then we have adjoint of a matrix. Let capital A is equal to Aij be a square matrix and B is equal to a matrix consisting of capital Aij, where Aij is the cofactor of the element Aij in the determinant A. The transpose B prime of the matrix B is called the adjoint of the matrix A and is written by Aj of A. For example, A is equal to 1, 2, 5, 2, 3, 4, 2, 0, 5. Then B is 15 minus 2 minus 6 minus 10 minus 1, 4 minus 1, 2 minus 1. And adjoint of A is transpose of B, that is minus 15 minus 10 minus 1 minus 2 minus 1, 2 minus 6 minus 4 minus 1. Now A times adjoint of A is equal to adjoint of A times A, that is determinant of A multiplied by identity matrix. So from this we can find out inverse of a matrix, which is adjoint of A divided by the determinant A. Inverse of a matrix A is denoted by A to the power minus 1. So I think we can stop here and we will study remaining theory in the next video. So we are left with the Hermitian and skew Hermitian matrix, more definitions. So more theory is there, not much is there, but we can't complete everything in this video, it will be too much. So we will cover the remaining theory in the next video. We will resume here at Hermitian matrix and skew Hermitian matrix. Now I will show you my website. So you come to ashtavakra.org. You can download algebra, trigonometry and geometry PDF from second, third and fourth link. Note that the downloaded PDF will not have date, so you can add this date to the downloaded PDF. And after 15 or 30 days, you can come here again and check the date. If the date has changed, you can download the PDF again and add new date. Also, this HTML format will go away because maintaining the typographic quality of both HTML and PDF is very difficult. And for the question answer forum, you can click on the 8th link and you will arrive at this question answer website. So I have created tags for you: algebra, calculus, connectivity, geometry, probability, trigonometry. And if these do not satisfy your tags, then you can use the generic tag mathematics. So if you enjoy human interaction instead of AI, you can come and ask your questions here. So I will link this video here, and I hope that you got something to learn and you find this video useful. So thanks a lot for watching the video. We will meet again tomorrow in the next video with the remainder of theory of matrices. Till then, I'll say bye and you have a nice day. Stay curious, keep learning, and most importantly, enjoy.